Hello students, today let us discuss the topic magnetic particle testing. So this is one more NDT method which we are going to learn. So now first of all, introduction to magnetic particle inspection. So this method is suitable for surface and near surface discontinuities in magnetic material. So mainly magnetic material is ferritic steel and iron. So this method can be used for detection of surface and near surface, so close to the surface. If there are any discontinuities or defects, it can be found with the help of this magnetic particle inspection, but the condition is that the substance or the component which we are testing must be a magnetic material. So mainly ferritic, steel and iron. So this method is suitable for detection of surface and near surface discontinuities in magnetic material, mainly ferritic steel and iron. So here this figure is illustrating or showing the principle of magnetic particle inspection. So what is the principle? So the principle is to generate magnetic flux in the component which is being examined. So here you can see there are flux lines produced. So this is the flux leakage. Okay, and these are the indicating particles. So how these flux is produced in the component? So here the flux lines will be produced and the flux lines will run along the surface at right angle to the suspected defect. So here flux lines will move or will pass through the component at right angles to the suspected defect. So if there is defect in the component or on the surface or below the surface, these flux lines will run perpendicular to the defect. So at 90 degrees these lines will be running to when we compare it with the defect. So if there are any discontinuities or if there are any defects, then these flux lines will stray out into the air at the mouth of the discontinuity. So when they approach a discontinuity, so here you can see these flux lines are moving perpendicular to this. Okay, so this is the crack. Here we can see it is moving perpendicular to this crack. Now when they find the crack or when they find any discontinuity, they will stray out or they will go out into the air at the mouth of the crack. So here, so we can see how these flux lines are deviating when they encounter a crack. So the crack edges becomes magnetic attractive poles. So this crack edges, so here one edge and here one edge, so they will become magnetic attractive poles. So this is the north pole and this is the south pole. So they have the power to attract finely divided particles of magnetic substances such as iron filling. So these poles will have the capacity to attract the magnetic particles. So here indicating particles. So what they will do, first we will produce a flux in the component. Then if there are discontinuities, there will be leakage of the flux and poles will be produced. So north and south pole. Then we will put some indicating particles, that is nothing but the iron fillings. So these poles will attract these iron fillings. So principle, it is to generate magnetic flux in the component that is examined. With the flux lines running along the surface at a right angle to the suspected defect. So when the flux lines approach discontinuity, they will stray out the air at the mouth of the crack. The crack edges becomes magnetic attractive poles, that is north and south pole. These poles have the power to attract finely divided particles of magnetic material such as iron fillings. So what are these iron filling particles? So these particles are oxides of iron with size range 20 to 30 micron. So iron fillings are usually oxides of iron with size range 20 to 30 microns. So how these particles are placed or suspended on the surface? So they are usually suspended in a liquid which will provide mobility or movement of the particle, that is the iron fillings, on the surface of the test piece. So assisting their migration to the crack edges. So these iron fillings are usually suspended in liquid. So they are mixed or they may be put on the surface of the component which we are testing with the help of liquid, so that it will be easy for the iron fillings for moving towards the crack edges. So they are usually suspended in liquid which provides mobility for the particle on the surface of the test piece. Assisting their migration or movement to the crack edges. So these particles can be red or black oxide, or they can be coated with a substances, that is the with fluorescence also we can coat these iron fillings so that they will provide brilliant ultraviolet illumination. So these iron fillings may be red or black colored, or they may also be coated with the substances which are fluorescents. When we get these particles in ultraviolet light, they will provide very brilliant or dark color so that we can observe them easily. So the particles may be red or black oxide, or they may be coated with substances which fluoresces brilliantly under ultraviolet illumination. So these particles are present as a great contrast as possible between the crack indication and the material background. So this technique, that is the magnetic particle technique, not only detects those defects which are not normally visible to the unaided eyes, but also they render easy visibility to those defects which would otherwise require close scrutiny of the surface. So here these defects which are not visible to our eyes can be detected with the help of this magnetic particle inspection. So this method renders or provides easy visibility of those defects which would otherwise require close scrutiny. So now, how do we produce the magnetic flux? So there are many methods for generating this magnetic flux in the component, but the most simple one is application of a permanent magnet to this surface. But this method cannot be controlled accurately because of indifferent surface contact and deterioration in the magnetic strength. So there are many methods for generating magnetic flux in the component. So the most simple one is we can attach a permanent magnet to the surface of the component, but this method cannot be used because we can see that there will be difference in the surface contact and that will deteriorate the magnetic strength of the component. So that is why modern equipments generate the magnetic field electrically, either directly or indirectly. So magnetic flux can be produced in the component by many ways, but most simple way so using this permanent magnet is not advisable because of indifferent surface contact will deteriorate magnetic strength. Modern equipments generate magnetic flux electrically, which may be either direct or indirect. So in the direct method, a high amperage current is passed through the component and the magnetic flux is generated at right angles to the current flow. So here there are two methods of generating magnetic flux in the component. The first one, that is the direct method. So here a high amperage or high ampere current is passed through the component and magnetic flux will be generated at right angles to the current flow. So we have to be sure that the current flow must be in the same line as the suspected defect. So therefore the current flow should be in the same line as the suspected defect. So in this method we must have some idea about the defect. So because we have to pass the current in the same line as that of the suspected defect, but in some cases we may not know where the defect is actually present. So in that cases we are going to use this indirect method. So direct method cannot be used in cases where we have no idea about the orientation of the defect. So indirect method is used. In such case, indirect method. So in this method, it can be done in two ways. So this can be done in two forms. First one is passing a high current through a coil that encircles the subject. So there will be a coil which is encircling the subject or the component, and through this coil we are going to pass the current. The second form of indirect method is making the test piece form part of a yoke which is wound with a current carrying coil. So making the test piece form part of a yoke which is wound with a current carrying coil. So this effect is to pass the magnetic flux along the part to reveal transverse or transverse and circumferential defects. So why this test piece? The test piece is nothing but the component will form a part of yoke which is wound with a current carrying coil. So if you see the figure, you will be able to understand what it actually means. So why this is done? It is done to pass magnetic field along the part to reveal transverse and circumferential defects. The effect is to pass magnetic flux along the part to reveal circumferential and transverse defects. So let us consider a bar whose length is greater than its diameter. Then the longitudinal defects can be detected by current flow and transverse and circumferential defects by indirect method of encircling coil or magnetic flux. So if you consider a bar whose length is greater than its diameter, then the longitudinal defects can be detected by the direct current flow in by the first method, that is the direct method. But if you want to find circumferential and transverse defect, then you have to find them with the help of this indirect method and by using this form 2. What is the form 2? It is nothing but we are going to form a the test piece will form a yoke which is wound with a current carrying coil. So the electricity that is used for producing this magnetic flux in any of these methods can be alternating current. So electricity used for any of the above methods may be AC current, that is alternating current, or half wave rectified direct current, or it may be full wave rectified direct current. I will simply write it as GC. So here this both of them are indirect methods, and this is the first form in which we are passing a high current through the, so this is the current is passed through this coil which is wound around the component. So if this is the component, and you can see here there are indications like crack, then there is direction of the field. So if this is the crack, the direction is perpendicular to this field. So here this is the direct method in which high amperage current is passed through the subject, and here magnetic flux is generated at right angles to the current flow. So if the current is flowing in this direction, then the magnetic flux is developed in the direction. So this is the direct method. So as we have already discussed, in direct method a high amperage current is passed through the component and magnetic flux is produced in the direction perpendicular to the direction of the current flow. So we have to make sure that the current flows in the suspected defect direction. So if there are cracks in this direction, the current must flow in parallel to these cracks. So this is the first method, and this is the second method, that is the indirect method and the second form. So in this we are making the test piece form part of a yoke which is wound with a current carrying coil. So this is the coil, encircling coil, which is carrying the current. So if there are cracks, you can see that this encircling coil is producing a magnetizing current. So in this method we can find transverse as well as circumferential defects. So this is indirect method, second form. So as I have told you, We can use AC current or half wave rectified DC current. So if we use AC current, the AC current generated magnetic flux, because of the skin effect, follows the contours of the surface and it does not penetrate deeply into the material. So if we produce the magnetic flux using the AC current, we can see that the magnetic flux will not penetrate inside the component. So only the surface defects can be detected when we use the AC current. So magnetic flux produced using AC current does not penetrate deeply in the component due to skin effect, and so we can detect only surface defects. So with the AC current, only surface defects can be detected. So this half wave rectified DC current will penetrate more deeply, but it is inclined not to follow sharp changes in the section. So here we can see that if there are defects somewhere here, okay, you can see there is change in section. So here there is, the diameter is less and here the diameter is increased. But if you use this half wave rectified DC current, then what happens is, it will, no doubt it will penetrate deep into the component, but if there are sharp changes in the section, it will not follow these changes. So penetrates deeply, more deeply, but does not follow sharp changes in the section. But this half wave rectified DC is useful for detection of slightly subsurface defects. So but it can detect slightly subsurface defects when compared to the AC current. So why do not we use this direct current only? Why half wave rectified DC and AC current is being used? No doubt DC current will penetrate more deeply, but it does not have this facility. What is that facility? DC current demagnetizing of the material after DC magnetizing is very difficult than with that of the AC magnetizing. So it penetrates even more deeply, but demagnetizing of the material after DC magnetizing is difficult. So that is why we do not use the DC current. So normally, to ensure that the test piece has no cracks, it is necessary to magnetize it in at least two directions. So we have to magnetize in two directions to check if there are any cracks in the material. So after each magnetizing, an ink application visual examination of the piece for crack indication is done. So after magnetizing, we have to check with our eyes to check to see if there are any cracks in the material. So here we can see a component after it has been magnetized, and it is showing us the cracks which are present in it. So here, after the magnetic particle testing or during the process of testing, we can see how it is indicating the cracks which are present on it. So basically magnetic crack detection, so recently they have developed magnetizing equipments. So the magnetizing instruments or the magnetic crack detection equipment will take two forms. So magnetizing equipments have been developed. They take two forms. So for test pieces which are which are part of large structures or pipes or heavy castings which cannot be moved easily, the equipment will take a form of just a power pack to generate high current. So here this magnetizing equipments will act in two forms. For large structures or pipes or heavy castings which cannot be moved, it will act as a power pack to generate a current. So this current is applied to the component either by contact rods on flexible cables or by an encircling coil, as we had already seen. So here the current is applied to the component or the subject which we are testing by contact rods or by an encircling coil of cable. So the amperage of the current which may be used by this component may be up to maximum of 2000 amps for portable units and 10,000 amps for mobile equipments. So current amperage used by these equipments is up to a maximum of 2000 amps for portable units and up to 10,000 amps for mobile equipments. So after the current is supplied, there will be magnetic flux produced, and then what do we do is the indicating particles which are suspended in thin oil or that which may be kerosene or water, that is nothing but the iron fillings which may be subjected to or which may be mixed with some liquid which will give a fluorescent lighting when they are subjected to ultraviolet radiations, are made to pass on the or they are made to fall on the surface of the component. So what do? They will adhere or they will get stick to the cracks if there are any cracks in the component, and they will, when ultraviolet radiations are passed through, they will give some bright coloration, and hence we will be able to understand that there are cracks in the component and their exact location also. Now, so here there is a realistic image of how the magnetic particle testing is carried out. So here there is a hook on which the testing is carried out, and you can see that there is a crack which is visible here. So this is before the test. Even this, so gear teeth, so we can find cracks here. So this is the image for showing how the test before and after the test, how do we find the image. Now, what are the advantages of this magnetic particle inspection? So the first advantage is simplicity of operation and application. And application. So the process is simple, and this gives quantitative results. So this can be automated. This process can be automated apart from viewing. That is nothing but everything can be automated apart from the viewing or the checking for the defects at the last stage. Now, what are the disadvantages? So, disadvantages say that this magnetic particle testing is restricted to ferromagnetic material. So, it is restricted ferromagnetic materials, and it is restricted to surface or near surface flaws. So deeper flaws or defects cannot be identified with the help of this magnetic particle testing. Surface and near surface flaws. So it is not fail safe. So in the lack of indication, it could mean that no defects or process not carried out properly. So not fail safe. So if we have failed to recognize the cracks, there is no indication in that. So if there are no indication, we will just conclude that there are no flaws, but still there may be flaws present in the component or process not carried out properly. So this is all about the magnetic particle testing. So here we have discussed the introduction, the principle, and advantages and disadvantages of magnetic particle testing. So I hope you have understood the topic. Thank you.